So good morning, everybody. So this morning's TST meeting for ONOS, we're going to discuss a proposal for vector-based link weights for path computations. Today, ONOS supports only scalar link weights, and this proposal is going to be driven by Pavel Likin and Andrei Komarov. So can you guys hear us okay, Andrei and Pavel?
Yes, we can hear you.
Okay, great. So who should I make a presenter? Do you guys, I presume you have some collateral for the discussion, right? Some slides or?
Yeah, Thomas, I suppose you can give presenter to me. It's Andrei Komarov.
Okay.
Good morning.
Yes, I'll make you a presenter. You should have it.
Yeah, thank you. Pavel, will you give us a short introduction?
Okay. Hello, everyone. We are working for Netcracker company, and today we would like to introduce a possible extension for the ONOS link weight mechanism. We write this proposal based on our experience of implementation our custom PCE model with additive constraints. So, Andrei, I think you can start and go through slides.
Yeah, okay. As you may know, telecom providers often face a challenge to provide a service to its customers, which is a subject to multiple optimization constraints, multiple optimization objectives, and maybe some constraints. So here's an example. For example, customer request to optimize latency and bandwidth. There are multiple approaches to solve this task, and the most common one is probably to implement a scalarizing function which will aggregate several different metrics of the network into a single scalar value. This approach is very common. It has very obvious, advantages. It's simply to use and easy to implement, and it's guarantees to find the solution from the Pareto optimal set. So, but during our previous works, we discovered that there are also some disadvantages, some drawbacks, and now I'll try to explain them a bit. Here they are listed, and the first one is that scalarizing function, there are maybe different scalarizing functions. There you can see linear and min-max function. For example, linear function is a weighted sum of different metrics. And the first problem with scalarizing approach is that we somehow need to choose those weighting coefficients. And by choosing the value of the coefficients, we basically choose the solution that we will get. Here is a small example. On the graph, you can see a set of viable solutions. Here we have two dimensions. We have two optimization objectives, some abstract W1 and W2, and we have a set of possible solutions. And by choosing one or another coefficients, we get one solution or another. One is marked green and one another with yellow. So the problem is how to choose those coefficients. One probably obvious solution to this problem is to choose coefficients based on the priority of the metrics. If one metric is more important for us than another, we can give a larger or smaller coefficient to it, depending on what max or min maximization function we use. So this problem is probably solvable. Still, I think it's worth to mention it. Then we go to another issue with scalarization function. Because we have different types of metrics. Here I listed some of them. For example, delay is an additive metric because aggregate delay of a path is the sum of delays of the edges that the path includes. So delay is additive. Contrary, there are some different types of metrics. For example, reliability. As you of course know, reliability is multiplicative. If we have two links and with some reliability, we should multiply them to get resulting reliability of a path. Another type of metric is concave or min-max metric. For example, it's a bandwidth. If, for example, we have a path with consisting of two links, and one link has spare capacity X and another link has spare capacity Y, we should take minimum of them to know the spare capacity of the path. So there are different types of metrics, and if we use scalarization approach, we should there's no other way than to aggregate both those metrics in one single value. For example, I just give a small example. We need to optimize spare bandwidth and delay. So we have to, normalize those metrics and to get a weighted sum. So we multiply by some coefficients and we sum those metrics. And by this operation, by scalarization, we are losing the type of the metric. If we so as I told earlier, delay should be summed across the path, and spare bandwidth should be taken minimum value. But if we aggregate those metrics in a single value, we will lose the type of concatenation that we should use. Feel free to ask questions if I maybe not clear enough.
I think this is clear. That makes sense.
Okay, thank you. So this is the second type of problem which we didn't find a easy solution to, how to calculate aggregated weight for a path. We can't use just one operation, just sum or just min-max, because metrics have different concatenation rules. So this is the second problem. And the last problem is inability to strictly prioritize metrics. In our works, we have faced some kind of a task which let me explain it in the example. We have two criteria to search a path. First, high prio is to try to avoid some edge, some vertex. It is marked with the E letter. And the second low priority is to optimize latency. If we use the same scalarization approach, so what we assign some additional penalty weight to this vertex, so that the overall weight of this path, upper path, which includes the E node, will be greater than the weight of the second path between. But as you can see in this example, the path SD have a very big latency. So because of the big latency value, depending on what coefficient we choose, we still might get the path SED as the chosen one. Though we really wanted to find the path SD because it doesn't include the node E. So this was the second or the third problem. Just by assigning appropriate coefficient, we cannot make 100% sure that we will avoid the unwanted vertex. Because, again, if I'm not clear enough, you can ask questions.
Yeah, at least it makes sense to me, unless somebody else has any question.
So those are three issues that we faced with the scalarization approach, and because of that, we had to look for some other approach to fulfill our needs, and we came up with the idea of vector weights. This approach, vector weights approach, implies that we that weight can contain multiple components, and each component represents one or several network metrics, and moreover, each component can have its own concatenation rule. So one component can be additive, another component can be min-max. I will show it a bit later. So we decided to try vector weights. It assumes that the objective can be ranked. Vector weights assumes that we can strictly prioritize our objectives. So if you wish, the first one is the most important, and the last one is less important. And two vector weights are compared using the lexicographical method. So we just compare them one by one. First components first, second, and so on. There we have several slides on implementation. I will skip them and go to pros and cons of vector weights. Vector weights help us to resolve those issues that I've talked earlier. Firstly, we can strictly prioritize metrics. So because of the lexicographical, the nature of lexicographical comparison, if we return to the example with this example, firstly we will try to search a path which does not include the node E, and only if we have several paths that don't, then we go to the second objective, which is delay in this case. So In this case, we will get took the node SD. Since it's the only node which doesn't include E, then it will be our result. So vector weights assures that we can strictly prioritize our objectives. Then we can handle metrics of different types appropriately. As I said, vector weights contains of many components, and each component can have its own concatenation rule. So if a component represents, additive metric, then it will be then the summation will be used for it. If it's concave, then min-max, etc. And the cons that we have shown, the obvious cons, is that there is no simple way to consider two metrics of the same priority, because by the nature of lexicographical comparison, we always take first, then take second. However, this in several cases this drawback can be, there is a workaround. If we have metrics of the same priority and they have the same concatenation rule, if we have, for example, several additive metrics, then we can combine them into a single component, into a single vector component. So this drawback sometimes can be, we have a workaround for it. That's for the vector weights, and a bit of changes. We have some kind of proposal of changes that we would like to see in ONOS. And the first one is probably, yeah, okay, maybe some questions.
No. It's perfect. I mean, I think at least I understand the pros and cons of the two different approaches.
Yeah.
I don't think the con, that's at least as far as the inability to compare two metrics of the same priority, I don't think that's a big deal. Yeah, like you said, there's workarounds, different strategies where you basically scalarize the portion of the space.
Yeah.
But
yeah,
I guess I'm really interested in terms of what your specific proposal is, because I would definitely think it would be great to get this in. The question is, how are we going to get it in without, while considering backwards compatibility and things like that. So I'll let you proceed. Go ahead. This is going to be good.
Okay, thank you. So basically, the first general change which we are proposing is to, everywhere in ONOS currently the weight is a double value, is a scalar double value. So in path search interfaces, in path interfaces, basically it's everywhere. So the first major change is to replace it by the abstract weight interface. Weight is some representation of a weight. Main requirement that weight can be compared to another weight, and it should be possible to concatenate two weights by some rule. And to maintain backward compatibility to your current design, first things to do is to implement Scalar double weight. It is an implementation of the weight interface, which inside will keep a double value. It compare method will simply compare double values. It concatenate method will simply sum up private double values. So to maintain backward compatibility, we have this. Of course, interfaces, link weight, edge weight, which currently return double value, we have to update them to return this abstract weight. And all existing users weight users, abstract graph path search, breadth first path search, etc., which currently expect double value, they will have to deal with this abstract weight. In search algorithms, the only things that we do with weight is basically compare and concatenate. So there is no much to change. The algorithms will remain completely the same, except that instead, just a simple plus for double, they will use concatenate method, and simple comparison, less or more, they will use the compare method. So we have a new interface, we have an implementation for backward compatibility, and finally we propose to try to maybe implement prototype of vector weights, as was proposed earlier, the weight which will have many components, from one to many. And there is a mock-up of changes, but I suppose it's maybe too detailed for now. Or if you want, I can go through them.
Okay, so in terms of in terms of preserving functionality, clearly the that you outlined on that previous slide, they would definitely, because as you said, the manipulations of the weights are fairly limited. It's basically just comparison and addition, combining.
Yeah.
There is not the code in the graph search algorithms is fairly contained to just several classes, so that will be really easy to update.
Yeah.
So in terms of preserving functionality, that looks like that's a great plan. In terms of sort of providing API compatibility, I guess there is probably no good way to preserve the backwards compatibility. At least I can't think of one. And this definitely does not, right? It does not preserve backwards compatibility. So I guess my question here is to the general, audience, developers or TST members here. How much of a problem is that in your opinion to break sort of our deprecation policy and backwards compatibility for these tool APIs? And clearly, I think there is a reward, right? There is a risk and there is a reward. I think the reward which is offered by this new capability is great. There is also some risk to this in terms of not necessarily in terms of increasing performance or reducing performance or increasing complexity. That's not the cost, but the cost here is in terms of potentially breaking backwards compatibility. And I would like to at least get a pulse from the general developer audience to see where they think the balance lies.
I kind of think, at least outward-facing API, like the past service kind of thing, we definitely should try to keep it as a deprecated, at least for one version, and that probably can be done if we get the scalar link weight, wrap it around in vector weight, and use a vector backend. That kind of thing is probably relatively feasible.
So Andre, I'm gonna give you back the presentation rights. Is that okay?
Yeah, go ahead.
Yeah, so I think we're in the middle of discussion. I think Yuta was saying, if I just paraphrase and I'll let you resume, that we should be able to maintain backwards compatibility for the APIs at the path and topology level. And then maybe at the library level, as far as the graph library, you could probably break that. It should be fine. But that's what you were suggesting, right?
That was what I was
So I'll let you resume. Go ahead.
Yeah, basically that was the idea. Probably we can write a wrapper at the past service kind of level, but if we try to maintain compatibility at the graph level, probably effectively we'll be copying, pasting all the code in the scalar version and vector version, which probably is not beneficial for everyone. So I think we should break the compatibility within that ON.Lab graph library. And the public ONOS API, we should try to keep the deprecation policy. I think that's what I was suggesting.
Okay.
Yeah, I completely agree with that. You know, cases where we have at the ONOS API level a double in a method, just keep that around for. I mean, it could even be a default deprecated method in the interface that basically just casts it to, or not casts, or encapsulates it in a scalar double weight and then passes it to the real method.
That sounds good to me. Because I mean, I like the proposed changes actually a lot. So,
Thomas?
Yes.
So I have a very basic questions about this vectors. So in your presentation, you gave an example to use the delay as parameters. You also pointed out you have a mixed mode. So do you have examples how you get the weight the vectors by combine the bandwidth, jitters, and delay, all these together? Do you have the example how to use that?
You mean in with scalarization approach or with vector approach?
I saw you have one slide to talk about the you can use the mixed mode. I forgot the which is which in somewhere.
Maybe you're talking about this slide. The slide was exactly about there is no simple way to combine different types of metrics into a single value. So with scalarization approach, there is no good scalarization function if we have different types of metrics like.
Okay, so the algorithm past calculations are still based on the single parameters, right? Like a bandwidth, if you based on the bandwidth. Okay, what's the requirement based on my understanding to the topologies? You need to store all these parameters. If the past calculation just used one of them, you was just based on that one to do the past calculation and bandwidth allocation, right?
Yeah.
Okay, so I'm not sure if that API probably is so you see the double parameters, double values. What do you mean the double value? The double value is the one is weight, another one is the what's the. I was trying to understand to me the past calculation now is become complicated. Originally, I was thinking you can abstract all the bandwidth and all those things, combine those together to generate the new parameters called the weight. Okay, so all the past calculations were based on that weight, abstracted value, not still based on the individuals.
So that was the point.
I think there's something I missed there. So now to me it's a complicated past calculation. If the one is based on the jitter, then we use this value to do the past calculation.
Yeah. So that coming up with that weight value from variable parameter is non-trivial, and fine-tuning that coefficient, coming up with a magical coefficient to do the weight function in a way you want to manage the network is difficult in certain conditions. So we want to keep each component we want to use as a past computation as a vector, bring it up to the end. Then we can prioritize the.
Yeah, reducing it to a single scale, you basically lose information, and the loss of information makes it difficult to do sensible prioritized comparisons. And so that extra information, which basically first of all by retaining the individual components of the weight, and also retaining that priority, gives us that additional information and additional possibilities. Actually, it will reduce the complexity if it's done correctly. And because you no longer have to do mental gymnastics or some sort of tricks to be able to stow that extra information away. So I think even though it looks like it complicates things a little bit, if it's done correctly, and I do like the proposal that's done in here, that proposal will map it nicely to allow us, basically by just substituting the weight for the raw double, right? It allows us to maintain the simple scalar value by providing the scalar double weight. But at the same time, it allows us to move into the more sophisticated realm where we retain all of the individual components. And the individual components is just arbitrary vector, and you decide what those components are and what their priorities are. And you decide what the operations, the comparison and concatenation operations are. And so you can, at the same time, compare certain things through the min-max or through linear some sort of linear manipulations if you need to.
Yeah, so the one concern for this is for the multi-domain case. If each domain they use the different weight calculations, right? How do we do that? So seems like okay. So we can define the vectors, the tables, matrix, right? So the different domain they might use the different matrix and they use the single controllers to control the multi-domains.
Yeah, but I think I think this is enhancements to the graph. First of all, graph utilities at this level, and at the API, the ONOS API level, like the path service and topology service, which have path finding services. Those all operate on a single control domain, right? And then if we do move to federation, space of federation, where we actually do need to be concerned with plotting paths through multiple different domains, I think we'll deal with it then, and that will probably be an Uber function anyway to be able to deal with, where basically the policies used within one domain to allocate paths versus across another, that will be abstracted away. And there will be a higher level pathfinding function which will summarize things either using scalar or potentially using a different vector. So I don't think that, I think that will be surmountable. That's not, I don't think that's an issue.
Okay, let me think about this.
Yeah.
Okay.
So then so Brian, you were saying you agree with this, right? It's no issue for you.
Yeah, no, I think there's definitely precedent for using, more proper object types or more descriptive object types rather than primitive values. So
yep.
On that side, I think this is actually definitely an improvement, even if you just were to use the scalar double stuff. We do the same thing for timestamps and a bunch of other things. So I think that's good. One other question that I had, which is more on the theory side of things, maybe. So you talked about the different types of weights that you may have, the concave weights, the additive weights, and the multiplicative weights. But have you found in your experience that there's sort of a difference between maybe some weights or constraints that are used to filter versus to optimize? Like, for example, you may say that you want to avoid a node with extremely high priority, but you may also say I want to exclude a node always. Like, some of the weights may be more binary, and I was sort of wondering how you could use more binary constraints to filter the optimization problem or reduce the optimization problem to some subset of the paths. Is that considered in this work, or would that be something additional?
It's some sort of additional. Actually, in our work, we are facing, as I said, both kind of tasks. We have optimization objectives, which we are talking about here, and also we have hard constraints. Exclude an edge with spare bandwidth less than X. So those two types of tasks, they are solved differently. For strict constraints, we use filtering. So we get the graph, we choose each edge for a bandwidth, for a spare bandwidth, and if it's the constraint is not fulfilled, we just simply remove the edge, but then we still may have an optimization requirement for a bandwidth. So we removed edges which do not fulfill the constraint, but we still want to choose edges with maximum spare bandwidth for for load sharing, for to use less occupied edges. So it's two different types of tasks, and we can't just by filtering we can't solve optimization issue.
Right. Okay, that makes sense. So you'd view the filtering step as one that would happen beforehand to constrain the problem, and then even some of the filtered constraints may still have entries in your optimization vector.
Yeah.
Okay, makes sense.
Yeah. So on a related note, today, for example, the multipath Dijkstra algorithm that we use essentially uses kind of in-band signaling of one of the illegal values of the weights. So basically negative weight signal filtering criteria. So I guess we would now, because it was a scalar value, it was simple to do. But I guess in this case, when we have a vector, how would you propose we signal the filtering, at least at low level of Dijkstra? Would we have like a non-value for the vector?
Actually, in how we see it, we apply filters before we construct weights. For example, we want to, filter edges with some bandwidth less than some threshold. Firstly, we run a filter, and it removes all edges with inferior bandwidth. And only after that, we go to optimization. We construct vector weights if we choose to use vector weights. So at this moment, we do not need to, to have negative values. But it's only our vision. Maybe there is another.
Which is so. I mean, I got that from the answer you gave to Brian. But because you're using your own algorithm, right? But let's say you were, let's say you wanted to use the built-in Dijkstra that we currently have in the ON.Lab app utilities, and that part of your algorithm essentially relies on negative weights because Dijkstra does not support negative weights, right? It could go in endless loop, and exploiting that. Perhaps maybe unwisely, but exploiting that, we basically use the negative values as basically a signal to filter the links out. They're basically considered non-traversable if the double value is negative. And so, in order to preserve at least that portion of the algorithm, and without having to explicitly filter them, as in filter them, as in remove them from the graph, right? We don't want to do that necessarily. We just want to remove them from consideration. So I guess we would have to probably come up with a mechanism that would indicate some sort of a decline value.
We didn't know about this particular situation, but I suppose we came up with something.
Yeah, I mean it's a low-level technical detail, but it just Brian's question reminded me of that. So is this something that you? So let's say we give it a go ahead, which it seems like we seem to have an agreement here, at least in TST side. Were you guys planning to proceed with this in the immediate future?
Yeah, basically we are some sort of implementation of it in our, user part, in our application part. But if there is a chance to, contribute it to the core, we of course would be glad.
Yeah, so I mean that would be great. So I guess I would suggest maybe starting with I guess it could all be delivered as one thing. So I guess I would let you decide how you want to proceed in terms of contributing. We definitely welcome the contributions. Of course, they'll have to be reviewed through Gary. And I'll let you make the judgment whether you want to review it in parts or whether you want to review it all together, I guess. Whatever is going to be easiest for you. I guess one note to echo what Yuta and Brian suggested, if you can, as you're reworking the path service and topology service interfaces, if you keep backwards compatibility in mind there, so that at least the old methods can be kept and just marked as deprecated, and maybe offer new methods.
Yeah, sure.
If that if that can be accomplished, that would be ideal. And at the API level, or at least at the library level, when it comes to the ON.Lab miscellaneous utilities with the graph package, I think there you can take more liberties and rework things as necessary, breaking backwards compatibility. Okay?
Okay.
So is there any other questions on this or suggestions from anyone?
I suppose we didn't. This would be our first contribution, so probably you have guidelines or something, for contribution. No?
Yeah. So I think this should be fairly well documented in our wiki.
Yeah. I'll share the link to the how to start contributing, how to use Git things.
Thank you very much.
Yeah, and then feel free to use the mailing list to, we can continue discussion on the mailing list on ONOS Dev. And that way other people can get visibility to it.
Yeah, I suppose we will need a bit of help, to get started, to get it rolling.
Yep. Yeah, so if that's the case, then maybe you could go, you could potentially just do it in pieces too, if you need to. Maybe just change the underlying graph APIs first. And underneath the hood, and then later on rework the APIs. I guess you can work in either direction, but if you want to do it piecewise, then you can get probably earlier feedback.
Yeah, that would be great.
All right. I like this proposal again. So thanks for offering to help with this.
All right, it's a pleasure.
So unless there are other questions or suggestions, I think we can probably end the meeting.
Nothing for me.
All right. Cool. And apologies for the interruption there. We'll start trying to figure out some better ways to do our conferencing. All right.
Thank you, guys.
And the meeting, and thank you very much, Pavel and Andrei. We'll talk to you later.
Thank you.
Thank you.
Bye.